Good morning, ladies and gentlemen. My name is Stephen Goslin. I'm the project manager for the Pirarucu team. Today we'll be talking about our Pirarucu mission and our endeavor for the Mars Moon's Prospector mission. We are from Embry-Riddle Aeronautical University and a preliminary design, spacecraft design team. Our team consists of 8 subgroups. Our team consists of 8 subsystems. These are attitude and orbit control systems, communication, mission planning, power, propulsion, science and instrumentation, command and data handling, and structures. Today we will be discussing the RASCAL competition we are currently entered in, the specific theme, science and traceability matrix, concepts of operations, and preliminary mission configuration. The Revolutionary Aerospace System Concepts, Academic and Linkage, sponsored by NASA, the RASCAL challenges are geared towards graduate and undergraduate students and aim to provide innovative approaches and strategies to the space exploration. Such revolutionary development may consist of reduced mission costs, promote future human exploration, and improve safety of future missions. NASA is looking for sustainable exploration programs that will collaborate with commercial and international partners for the most optimal mission configuration. The mission that Pirarucu has chosen is the Mars Moon's Prospector mission. This mission has asked us to explore 1 or 2 of the Martian moons to fill in strategic gaps. Little is known about the moons in our team. It is primarily tackling the origin of the moon, environmental characteristics, and human exploration. All this must be constrained to 3 years starting from the year 2022 and cost no more than $300 million, excluding the launch vehicle, and extended missions have been encouraged if they are practical. I'm now going to hand it over to Jean Marie to talk about our science traceability matrix.
Hello, I'm Jean Marie. I am the team lead for science and instrumentation. As you can see on the screen, our science traceability matrix follows 3 strategic knowledge gaps, namely the origins of Phobos, the environmental characteristics of Phobos, and whether or not human exploration is feasible. Our first objective, covering our first strategic knowledge gap, is going to survey the general composition of Phobos and give us a density, composition, elemental makeup, and radiation concentration of the moon. Our second objective is following our second strategic knowledge gap, namely topography and stratigraphy. It's going to determine the surface topography, internal substructures, and geological history, and basically give us a map. Our third objective, space operational hazards, answers if human exploration is feasible on Phobos and give us an idea of the dust density, the gravitational field, the radiation from surface scattering, and the regolith mechanical properties. On this slide, you can see our candidate instrumentation for whatever our measurements that we're going to be taking. Our blue instruments follow our first objective. We have SAM, which is going to be taking our densities and composition. We have Chemin, taking composition and concentration of elements and materials, along with Pixel. And then we have our radiation assessment detector, RAD, giving us energetic particle spectral analysis. Our green set are for the instrumentation for objective 2, topography and stratigraphy. We have cameras, laser, and radar, which are all giving us surface topography and landing sites, along with RIMFAX, which is going to give us our geological underground structures. The rangefinder and the surface stereo imager is going to give us an idea of global shape and rotational state. And finally, we have our objective, which is going to be checking for human exploration on Phobos. We have our cosmic dust analyzer, particle density around Phobos, seeing if it's possible to get close to the moon in order for humans to land. Our radio science subsystem, accelerometer, and gradiometer, giving us an idea of gravitational field for future missions. Chemin, SAM, and Pixel for regolith composition, see if landing is possible, and our radiation assessment detector to seeing if possible harmful radiation on the moon.
Okay. I'm now going to hand it over to Maggie Meyer to discuss our concepts of operation.
All right, so we have a multi-spacecraft mission. Our mothership has a bus which provides power, propulsion, communications, and attitude control. It carries 12 CubeSats and instruments as well. The CubeSats consist of the A-team, which has surface science instruments, the 7 dwarfs, which does surface sample retrieval and carries the surface samples to the mothership, which will also stock and refuel with the mothership. All right, so this is our storyboard. We have a launch day of September 22nd, 2022 on a Falcon Heavy. We will plan on injecting into the Mars transfer trajectory with an escape energy of 18.3 and a type 1 transfer ellipse. We will cruise to Mars, the nominal duration of 5 months and 9 days, and arrive at Mars on March 31st, 2023 with a highly elliptic orbit. We'll then phase with Phobos, acquire relative orbit, and commence remote observations. We'll deploy the A-team to perform the surface science at Phobos. The A-team will perform the surface science, and the mothership will relay this data back to Earth. The dwarf team will be deployed to retrieve surface samples and bring them back to the mothership. The dwarf team will make contact with the surface of Phobos and commence the sample retrieval. The A-team will return to the mothership to refuel, and the dwarf team will also return to drop the samples to the mothership. We foresee the dwarf team being able to make several trips back and forth before refueling. The mothership will perform sample analysis, and one member of the A-team will stay behind on Phobos to continue exploring. The extended mission will repeat steps 5 through 11, which would be the phasing of Deimos, and performing remote observations from the mothership, and then to deploying CubeSats, and returning with surface samples of Deimos to the mothership to test and relay information back to the Earth.
I'm now going to hand it over to Travis Snow to talk about our preliminary mission configuration.
As stated before, we are looking at a Falcon Heavy that will be able to carry 12,000 kilograms of payload to Mars moon, Phobos, and an estimated cost of $85 million. The structure design we have is using 3 ESPA rings that will carry the CubeSats, the propulsion, and instruments. Communicators of a Ka band for Earth communications and a NET-T network for inter-spacecraft communications. This is the preliminary structure that we have designed in CATIA as of right now. We have an ESPA ring of 157.48 centimeters in diameter, a height of 182.88 centimeters, and the CubeSats are going to be 12U with a dimensions of 24 centimeters by 23 centimeters by 36 centimeters. The light band will be used detaching the small satellite to go explore Phobos. Oh, and the bus rings are as shown as the S ring.
I'm now going to hand it over to Sarah Williams to discuss our communication side.
All right, so what you're looking at now is a preliminary communications architecture, and we can see how the CubeSats are going to communicate with the mothership using the L3 micro CDL, and the mothership will communicate to the Earth using a Ka band radio. We'd like your input on maybe some suggestions for what specific ones you have.
And thank you all very much for listening. We are the Pirarucu team from Embry-Riddle Aeronautical University. Are there any questions?
Because we have about 50.
We have a lot of questions.
We have about 50 questions for everyone.
All right.
We have questions. Would you like to ask us your questions first, or have us ask you our questions?
Okay. Yeah, we'd like to ask our questions first, if you don't mind.
Certainly, ask your questions.
All right. So from our yeah, there's a lot. From our attitude orbit control systems, I'm going to go ahead and let Brett ask his question.
Sure. This is Brett. The first question, we kind of discussed this in class today, but what sensors would be needed to accurately perform attitude determination and I guess guidance at Mars if there's no GPS to really determine our relative position.
Would you get closer? Would you get closer to the mic, please? We can barely hear you. Thank you.
Read mine.
Well, the first question, and like I said, we kind of talked about this in class today, but what sensors will we need to accurately perform attitude determination and the guidance, navigation, and control part of the mission once we leave Earth, as we're no longer going to have something like GPS to give us a relative position to Mars or Phobos or whatever object we're interested in looking at?
Dan Hagel with Blue Canyon Technologies. I'm the G&C lead. Yeah, once you leave Earth, really the only option you have is either sun sensor or if you don't need much attitude determination. But for what you're trying to do, you clearly do. So in that case, you're forced to go stellar-based, so star tracker. There are a number of products out there. We have one that's probably the highest precision system out there. Others are coming along as well. And then in terms of, you mentioned since there's no GPS, some systems use tone ranging to determine their orbit distance and such, but the one method I've seen the most recently is where they're using planets and the sun and the Earth. So you're basically doing triangulation. So instead of having a GPS constellation around you, like down in low Earth orbit where you've got these satellites at known locations and you triangulate with them, you're doing optical measurements with planets around you and do optical measurements using the star tracker. So there are a number of missions involved in that. One of them is Inspire. That's going to be launched in spring with JPL. Our star trackers are on those two spacecraft. They'll be taking pictures of the Earth-Moon system and planets to try and prove that concept in flight. There's some other missions that are talking about as well.
Okay, thank you very much.
Identify yourself.
Hi, this is Charles Norton from JPL. We're still working on a launch date for Inspire.
Okay, I assumed I heard it was spring, but okay. Hope you get it soon.
So I'll just answer briefly. I mean, we've looked at this problem for the moon. Mars is obviously a major challenge. But one option for you, because you're looking at multiple CubeSats plus essentially a mothership. So with a mothership, you can consider that to be your local DSN. So that could potentially be your communication hub and your nav and tracking support hub. And then the DSN that only has to communicate with one asset. Trying to communicate directly to the Earth with all of your CubeSats, there are 12 of them, would be challenging. So on your mothership, I'm just curious, well, you don't have to ask the question now. I can ask it in question period, but what you're looking at for the mothership, basically for guidance, navigation, and tracking in transit from Mars, and how you can potentially continue to use that once you actually get to Mars moons. Certainly to support your local CubeSats, which will require some guidance. And then, as Dan Hagel pointed out, there's attitude control systems that are available, extremely compact now from Blue Canyon and others too. That could allow you to do attitude control in your CubeSats, which is going to be critical if you're going to be taking samples from the surface. Anyone else want to weigh in on that? You guys want? Is that good? You think is that useful information to you guys?
Absolutely. Thank you very much.
Would you like to ask your second question?
You want to ask your next question?
Yeah.
I guess the next two questions that you can see there are going to depend on kind of the requirements we set for the mission. But for something of this, a mission of this type, would the RCS thrusters that control the attitude, would those maybe suffice for the orbit control thrusters too, or would we need another set of thrusters for that, possibly?
We'll get thrusters alone suffice, or would you need a combination of RCS? Okay, when you can't use, oh, sorry, go ahead, please.
Yeah.
Please, Dan, go ahead. You're the expert.
Well, I guess it depends how big the thrust. When you say for orbit control, you're talking about orbit insertion, or are you assuming that the mothership does the orbit insertion, and then you're talking about just orbit maintenance for the CubeSat? Question back to
Dan asked you a question. Did you hear that?
Yes. When we're talking about orbit control, we're talking about a couple things. That is like you said, orbit maintenance. It also is orbit insertion, but then it's also on the CubeSats themselves, getting to and from the mothership to the surface and back. That's pretty much.
For that type of activity, small orbit maintenance maneuvers, the thrusters that would be used for desaturation would suffice. Situation where you get into orbit insertion, you're requiring a huge amount of delta V at one time. So that's where hopefully the mothership is taking care of that for you. But if you do need some large amount of delta V, typically those thrusters are not sufficient for your desaturation. They tend to swamp the system because they put out so much force, which you need to very quickly decelerate and then enter into the desired orbit. But for routine kind of moving around between the mothership and other locations, then it would be fine. It's just a matter of how long you're willing to take. You know, if the small amount of thrust that would be good for fine momentum control would not necessarily get you to a new orbit right away.
Mars moons are pretty small. They're like asteroids, so it should be possible with a very modest thruster system to do that. And Warren James back there has a question. Oh.
This is Glenn Cameron from Maryland Aerospace. One comment I would make is that particularly on a spacecraft that small, one of the problems you're going to have is carrying enough propellant to do all the things you're talking about. So you're going to need to do an evaluation whether or not you can use electric propulsion for a lot of these types of maneuvers and do as much as you can with electric propulsion in order to get by with a lot less propellant, which means you may actually need two systems, one electric and one chemical, where the chemical, you know, whether it's hydrazine or something else, is the things that give you a lot of thrust in a short period of time, but a lot of your astronavigation is done using the more efficient electric propulsion.
Warren James?
One thing you might consider on the little satellites that go down to the Martian moon, you might be able to connect them to the mothership with a tether. And then you could use a tether to retrieve them and things. And that might cut out some of your propellant, might also open some other opportunities.
That's an interesting prospect. You know, the hardest, a big delta V expenditure also, I mean, your mothership, I assume, is going to have a more or less conventional chemical propulsion system. Is that correct?
Yeah.
Okay.
Yeah.
So
well, it's to be determined still, but most likely, yes.
Yes, it's going to be the instructors tell them so.
So, yeah.
You know, I mean, in the end, it's going to be a NASA competition, so we want to be a bit forward-thinking, but also be conservative. So, yeah, we're going to mostly have hydrazine or chemical propulsion on the mothership. And now I want to make a comment here. We have quite a bit of heritage. We're working on a proximity operations for a mission for the Air Force, the Air Force University Nanosatellite Program, and we have a 6U CubeSat that can carry about 75 meters per second in cold gas propulsion, cold gas propulsion system. So we plan to use that heritage on the CubeSats here. The tethers are interesting, but they might be a bit, we have to look into them. It's a quite interesting proposal. Maybe we'll have some other probes just going down and doing some elevator work on the moons. It would be pretty cool.
Cool.
Okay.
Shall we move on to the next question?
Sure.
Yeah, definitely.
And then just the last question here that I'm going to ask is the fourth bullet point there. Would it be possible to do completely autonomous attitude and orbit control, or would we most likely have to do a combination of ground-based and autonomous control to complete the mission?
Well, that depends on the degree of autonomy that you build into your spacecraft. I'd like Mike Riley to answer that question.
Thank you. This is Mike Riley, Riley Systems Technologies. I think that you're going to have to go into this pretty much looking at autonomy is the default for your approach. Your time of flight, your time of flight for communications has a huge latency there. So things are going to happen and they're already going to be done by the time you find out about them. So you're going to have to be very careful about that, though. So that's a very serious question. I'm sure that some of the JPL folks here might be able to say a little bit more about that, since they've actually had experience with putting spacecraft into orbit around Mars and having them operate there. So, but fundamentally, you're going to have a high degree of autonomy to make sure that your pre-planned operations and behaviors are carried off, and that when contingencies occur, you essentially have something that fails over to a safe, fails over to something that is fairly safe. So you have to come up with a complete strategy for that, but the default is going to have to be a high degree of autonomy and an ability to deal with faults and failures as they occur. So, you know, I don't know that a combination of ground-based and autonomous control is necessarily the right way that you would put that, because as soon as you let a little bit of the ground-based come in, particularly with the latencies and the catastrophic errors that could happen, you're going to have a system that pretty much is able to protect itself when things happen. And so that's a really big question there, and it needs some serious thought.
Thank you.
Anybody else like to respond to that?
Well, let me add something here. This is Bogdan again. Well, Michael, nice to hear you again. We were actually thinking of having something like pre-planned landing sites for our CubeSats that they can actually, so that will be the ground control, not necessarily in the loop, but pre-planned landing sites with a priority list, and then let the CubeSats land whenever they can, given lighting conditions and so on and so forth, with autonomy. So we're going to take your advice and go from there. Actually, thanks.
I think that's it. So do you have other slides, or is that it?
We have actually 8 more or 7 more slides of questions.
Okay.
I'd like to ask a question, and I'd like to ask you what your thinking is about the sampling mechanism for your CubeSats. Have you thought about that, and what concepts have you sort of floated about the sampling mechanism itself?
Well, right now we're using both SAM and Kemin, which I believe they have their own system for.
So you're going to have, I mean, those are fairly large systems. Mm-hmm. You're going to have all the sample handling on the CubeSats that SAM and Kemin require. You know, there are systems that don't require sample handling that'll get you that kind of information.
Yes, we're also considering those. These instruments have been our first round of candidate instruments.
Well, let me recommend a combined XRD system that I'm working on, which I can talk to you about in some more detail if you wish. Awesome. That doesn't require any sample handling. Okay. Of course, you know, the idea. I mean, you also don't know how much you've got in the way of rocks and how much regolith there. But there are a lot of newer instruments that have come around that actually could give you in situ information with, you know, because the mechanisms part is tricky with CubeSats. It usually takes a fair amount of power and volume. So you want to think about that. That'll be an important challenge for you guys to deal with in the future.
Right.
Anybody else comment on that?
We were thinking some electrostatic mechanism to pick up dust or regolith and drop it in something that looks like Kemin. And we know we have to do this in free fall. So we also have, you know, I mean, we are aware of the challenges, but the simpler the instrument or the simpler the processing, the better. We are not just familiar with those instruments. So any instrument that we can replace Kemin and SAM are more than welcome.
So are you going to have like, I was thinking that your instrument ring would have SAM and Kemin back at the mothership and you'd be delivering samples? Is that an architecture?
Yeah, right. Exactly. Yep.
I don't want to monopolize. Did you have a comment, Mike?
And we might need to spin it, you know, to make because on Mars, Kemin and SAM rely on Martian gravity to feed the samples down to the test chambers. We might need to spin it or do something smart about it on our mothership.
Charles Norton?
Oh, yes, this is Charles from JPL again. Yeah, you just touched on the question I was going to raise earlier. SAM and Kemin would not be options. on your deployable.
Okay.
Not on the CubeSat.
Yeah,
right.
but certainly, possibly on the mothership, that's a potential. But one thing that I didn't see in the presentation, which you'll have to address as well, are the planetary protection requirements that are associated with any type of mission of this kind that will touch the surface. Is that something that your team is familiar with or has started to look at?
Well, we know we need to cook this to 500 or 600 degrees. That's all we know about planetary protection. But other than that, we should look into it for sure. Yeah, thank you for pointing that out. Now, does it apply to Phobos and Deimos too? I guess.
It applies.
Yeah, it applies basically everywhere.
Everywhere. Okay.
Okay.
Okay. Thanks.
Yeah, you thought you were getting off the hook because it wasn't Mars, right?
Right. Right.
All right.
Russell, how much time do we have left?
15 minutes.
If somebody else has a comment, then we can choose you can ask probably about 3 or 4 more questions. We have one more comment in the room. No, it's good.
Hi.
This is good. Yeah.
Hi, this is Eric Dahlstrom. One suggestion about dropping these CubeSats on the surface, you might just accept that they'll go down randomly, and you might look at the Russian example of with their Phobos mission of having a little kick stick that then hops them around along the 0.3 milli-G environment. And also, since the escape velocity is only 5.6 meters per second, so the going back and forth to the to orbit is not going to be taking a whole lot, but it's going to be a very slow fall down from orbit around Deimos. So you might look at all that that together. But I think just if you have enough samples and you scatter them randomly, I think that's pretty good. You don't necessarily, and you know where you are afterwards. You don't really need to target so much.
Yeah, that gets at the need to know where you are. You can think of this as a traverse. You could think of it, because it's a small enough object, you can think of basically collecting these samples at known positions to get sort of a cross-section or a traverse, either one. You could control it to that extent. Warren, James?
Yes, one other thing to keep in mind, if you launch off the surface of Deimos, it's not just enough to have the delta V to get off the surface and escape Deimos. Once you've escaped, you've now got to do your prox-ops operations to bring the 2 spacecraft together.
Right.
And that can end up costing as much propellant as getting off Deimos, because it takes just 2 butterfly sneezes and you're gone. Mm-hmm. So keep in mind the prox-ops delta V and propellant cost could possibly be more than what you were going to be spending on just getting off Deimos.
Were you guys online to listen to the presentation that Dan Scheld gave on the hummingbird concept?
No, we were in class.
Right. Okay. So you might look on the website basically and pull up that presentation, and eventually it'll be available as a recorded presentation as well, to look at someone's concept for sampling asteroids that the group at NScience has been developing over the last several years.
Thank you.
Okay, why don't you guys pick a few burning questions, and we'll try to answer them in the remaining time we have.
All right. Let's go.
Go on to the.
Okay, so
do I have to change the slide? Are you changing the slides, or am I doing it?
We're changing the slide.
We're going to go ahead and move to our science and instrumentation section.
Okay.
And
yes, one of my questions up here was about how SAM and Kemen are pretty massive instruments, and how we can try to find something that does essentially the same thing but significantly smaller. Right now we have our CubeSats gathering samples and SAM and Kemen on the mothership, but they're still pretty massive instruments.
So you might think of a simple kind of sampling device. You might think of some electrostatic mechanisms for sample collection. You might simply think of your CubeSat as a sampling device only that would then retrieve these samples and bring them back for analysis. That's a possibility. That's one architecture. You might possibly think about putting on a small in situ measurement instruments that could give you some, data potentially. We talked earlier today about fiber optic spectrometers, for example, that are very compact. We're developing a very compact broadband IR instrument, and a lot of folks now are thinking about very compact instruments that could give you some local remote sensing. And then I mentioned the combined XRF-XRD instrument that we're developing. It's been developed to relatively low TRL at this point that does not require any sample preparation. That would be very good for getting the origin of rocks with virtually no preparation whatsoever. It's still a little bit on the large side for a CubeSat instrument, although we're working on making it more compact. But there's a lot of MEMS level instruments, including MEMS-based mass spectrometers, for example, that you could potentially use on board your sampler to give you some in situ context. And then if you want to do more sophisticated analysis that require special polishing and grinding, take your samples back to the instrument ring and offer the samples up to the instruments that are on board. These are just a couple suggestions. I'm sure other people in the room might have comments and more things to say. Charles Norton?
Oh, hi, it's Charles from JPL again. And just on the issue of MEMS components, one thing that we and others have seen on some launches is you have MEMS components on your CubeSat, and if they're exposed to helium during the helium purge at the launch site, you could lose those components. So, that's something to consider.
Thanks. Thanks for sharing that. Yeah, Mike Riley, and then Russell Cox.
Yeah, this is Mike Riley again. One thing that might help you out with some of these questions here is to think about the notion of a distributed spacecraft, where you have a control strategy in which you're not programming just each individual spacecraft, but you're programming your constellation of spacecraft. And that you're going to be bringing in that's going to put some emphasis on the sort of communications infrastructure you have between the two, inter-spacecraft communication, and how you're going to be managing the different computations that you have going on the different spacecraft. But that might be something that you might want to look at when you're trying to figure out how to command and control your set of spacecraft. Another point over there I see on the slide you talk about, is there a better instrument than the radio science for better accuracy? And I think some folks who are interested in laser and radio can perhaps help you out on that. I think it's going to be hard to beat radio science for some of the value that you get for the weight and energy that's going to use. But you want to see if somebody can do better, say, with laser ranging between the different spacecraft that you have. So there's some trade-offs there. But again, the fundamental point I was getting at before was maybe you can come up with the concept of operations in which you're programming a constellation of spacecraft rather than just each individually.
Russell?
So
and then Bill.
A radio question. Courtney, do you have anything to chime in on that one? That sounds like right up your alley. They were just asking, what can you do better than standard radio science for either communication or doing radio science, laser or some other frequency? Or
Yeah, no, I basically agree with Dan on that. That's why I didn't say anything further. But I'm going to talk to him later.
Okay. So there's JPL has a little Phobos hopper. Did that get as far as sample collection and handling?
He's talking about
Bob Staley's presented a few times.
Oh, that's right. I remember that concept.
Yes, this is Charles from JPL again.
Is there a place where we can find out about these instruments that you mentioned, Pamela? Because I told you we're not science, planetary scientists, yes. We're aerospace geeks. So we don't know much about instruments. We went to Kemin and Sam because we found them readily available on the website of Mars, the Curiosity rover. The same with Pixel and Impacts.
I can get you that information. And we're about to publish a paper, so yes.
Okay, excellent. Thanks.
You're welcome.
Yeah, there was a concept that Rob Staley at JPL and Jordi Parksari and his students at Cal Poly San Luis Obispo had explored at a Keck Institute for Space Studies Science workshop at Caltech, but not the workshop that I led, which was looking at a sample return mission associated with a Mars orbiter flyby, where there would be basically a solar sail-based mission which would deploy down to either Phobos or Deimos, do a soft landing, take a sample, do a gentle rise, again using the sail, and then be captured in the moon orbit. And it was just a concept that was studied. As far as I know, it hasn't been proposed anywhere. It was really just exploring the utility of a solar sail as a mechanism to enable that type of touch-and-go, land and rendezvous architecture.
There's a paper published on that, and doesn't Rob Stilly have a paper on that? And AIAA, it was from AIAA's, the space meeting a couple of years ago.
It's very possible that he does. Some of these have flown out of his NIAC, NASA Institute for Advanced Study.
There was a NIAC paper, I remember it.
He did have a paper which did discuss the general utility of small satellites as a mechanism for deep space exploration at lower cost. And it is possible that this was one of the mission concepts that was described.
It definitely was, and Bogdan, ask me if I forget to send you a copy of that paper, okay?
One question I wanted to address is is human exploration feasible? Is that incorrect for the measurement requirements? And I think actually all the pieces are there to actually answer that question, but it's an environmental question. For example, they were going to fly RAD, and RAD detects high-energy radiation, so they're going to measure the radiation environment, which is in fact a high HEO strategic knowledge gap.
Mm-hmm.
The other thing that they had on there is they had a cosmic dust analyzer, and actually cosmic dust analyzer measures micrometeoroid impacts. It's not really great for the regolith, but it's really great for detecting hypervelocity impactors, like above about 1.5 kilometers per second. So in fact, then if you include CDA, you now actually have are measuring the micrometeoroid and secondary impact ejecta environment around the moons. So they can do it. I think they just need to rewrite or rephrase. The payload's already there. They just need to reconnect it in a different way.
Mm-hmm. There's a couple other questions in the back of the room. Yeah.
Hi, it's Chris Craddock with RocketStar. I have an advisor to my company that owns a patent on a autocorrect for satellites using LiDAR and radar. So in thinking about whether or not you want to go autonomous or not with your radar constellation, your satellite constellation, I was thinking that this might be helpful in just taking that out of the equation, just letting it do it by itself. You can work on all the other science that you're planning to do. If you want, I can put you in touch with him, but I'm not sure if this would take away from your budget because he would probably want you to license the technology from him.
That would be great, thanks. And it doesn't matter. I mean, we have $300 million to spend, right? So, so from us, it's no problem. It would be nice to include some of the new technology that we can use for asteroid exploration later on, and maybe sample retrieval too. Yeah.
Okay. Warren James, V Infinity Research. Two comments on different threads in this conversation. One is, in terms of human exploration, probably the most important observation you could make relating to human exploration of Mars is to characterize the amount, distribution, quantity, and state of any water that's available on the Martian moons. Is it free water, bound water? What form is it? Because if you can find significant amounts of water on the Martian moons, which many people believe is likely, then the Martian moons become an extremely useful source of ISRU propellant for getting to and from Mars to the Earth. And it's probably the single highest leverage observation you can make. And so if you could characterize definitively amounts, kinds, states, etc. for water on the Martian moons, that could totally change the picture for human exploration of Mars. So a focusing of at least some instruments, some subspacecraft, some part of this mission on that could be just incredibly important. Second observation, you're basing the spacecraft on using an extended ESPA ring as your structural backbone. I think that's very inefficient. The ESPA ring is designed to support a very heavy payload sitting on top of it, which means its load case is designed around having something like a 10,000 kilogram load sitting on top of it under multiple G's of acceleration. That means you're taking to Mars a structure that is hugely over-designed for what you're doing. And so I think you would get a much more efficient design if you didn't base it on using the ESPA ring as your structure, but merely carrying your spacecraft to LEO within the ring or as a set of connected foldable elements that go around the ring, but don't use the ESPA ring for your main structure because you're carrying a ton of weight to Mars that you just don't need. Thank you.
Thank you for that. So yeah, I was just going to point out this is exactly why we created this workshop. Here we have an engineering team with not a lot of prior experience with science and the actual objectives of why would you fly one of these satellites anywhere. And we have a lot of people in this room who have some pretty interesting answers to that question. So this sounds like it's very productive. I really like it. And then the upshot, Pamela, is you have 10 minutes to wrap the discussion, and then Bonnie's going to wrap the session.
Okay. Great. Well, I think it's a very interesting exchange, and in the context of the talks that we just had, too, where there's some very interesting science things that need to be done, and people approach these from very different angles. So let's see, I'm back here, if I can. So we talked, basically to wrap up the session, we really gave an introduction to the idea of going from science requirements to mission concepts, which we will further with the people who gave presentations today, this afternoon. We started off talking about that a little bit as kind of an introduction to this afternoon's design challenge. And then we basically had the presentation from students at Embry-Riddle. Thank you very much. Very interesting. We've been working with some folks actually at JPL to come up with a concept for a Mars mission, which includes a popular architecture, which is a mothership with CubeSats that can be deployed in the environment. And the discussion basically gave us an opportunity to talk about some of the implications of the different kinds of architectures that we can use. So, questions which everybody is going to have are, and this is a big one, is really knowing where you are, and how do you know where you are, and how do you control where you are. One of the challenges of CubeSats when they get beyond low Earth orbit that everybody who does deep space CubeSats has to deal with is, low Earth orbit allows people to do attitude control because they can use the Earth's magnetic field, for example. They can use the fact that Earth is a large gravity well, and certainly on Mars, but particularly Mars moons, which are basically like asteroids. That's not the question. That's you don't have that. So active attitude control, knowledge and control is a challenge. But the good thing is that there are compact attitude control systems, and actually at this point, because of the work that's been done that's being done now to allow deep space CubeSats to develop to meet their mission goals, there are very compact propulsion systems, and you will have, in a few years, you will have options on what propulsion systems you use. And you can use them in micro-thruster mode to do, basically small movements or attitude control itself, or in transportation mode to go from point A to point B, using low energy trajectories particularly, and that's going to be discussed tomorrow, basically trajectories that require very little fuel that can get you to your final destination. We talked a lot about the kind of instrumentation, where it should be, where you want to put your mechanisms. This is a very important piece, and actually instrumentation is really kind of a bridge between the science goals and mission concepts. In order to meet the science goals, which we talked about here, including volatiles, very important for ISRU, and for understanding actually the formation of regoliths, solar system processes, and biological processes, I believe, too. Understanding water dynamics, water form, and it isn't just getting an ice pick and trying to grab a sample of a chunk of ice. There's adsorbed water. There's bound water in the mineral structure itself. And getting a sample back to look at it, you can discover these things, that they actually exist in the regular gas cell. 5 minutes, right? So the whole question of where you put your instruments, and if you have a multiple CubeSat concept, you have the option of either flying the same instrumentation on each of your CubeSats or flying different instrumentation. And I love the idea of multiple platforms because it means you can really you can provide a context for whatever you grab. It isn't a grab and go thing with one CubeSat. You could potentially do what geologists like to do, which is basically you and geologists typically do a traverse where they cross an area. They basically draw a line and take measurements along it, something that crosses several different types of terrain, and is sampling basically what's going on underneath. So the idea of actually doing that multiple measurement thing, as long as you know where you are on the surface, is actually very powerful. Even equipping, we talked about, whether you want your CubeSats to be sample collectors or armed with some instrumentation. Well, I would say that nowadays, because they're extremely small instruments, you might be able to do both, have sample collection and get some in situ data. They're going to be very compact spectrometers available, for example. And while you're doing that, the mothership can be doing basically remote sensing, can be doing sample analysis. So that's actually a powerful architecture. Before we get to the point where we have completely autonomous swarms that can do multiple platform things together and act as virtual communication or virtual processing nodes. And let's see, we got 5 more minutes here. So, would anybody else like to comment on the discussion that we've just had? I missed anything?
Well, I'll just say, and I think something I said early on, I think it would be helpful for these guys if they also took their instrument complement, wrote it down, and worked the other way out to their objectives, because then they get, they would thread, they see where things connect up even better in human exploration. SAM could help get the water, for example. And so that's a really good point, the models. They
started with certain instruments because those instruments are known and they're published, and the people that they're working with are very familiar with them. But it would be very good to actually do a literature search on the kind of instrumentation that's been developed for CubeSats. And there are Mars instrument development was relatively well funded in planetary science for a long time. So you could look at what's come out of the Mars instrument development programs in the way of very compact instruments. And there are a lot of them that you could potentially put on board. And then think about interesting mechanisms for sample collection. There are several missions that have been flown in planetary science that have used different asteroid sampling mechanisms, have used a variety of instrument sampling mechanisms. And one of them that hasn't been tried out yet is electrostatic dust collection, for example, which could be very interesting because there's a lot of information in the dust. Oh, yes, Charles.
Oh, yes, Charles from JPL. I just wanted to say it's very nice work. It looks like they've really addressed a lot of the major questions and looked at a lot of the major design considerations. So just wanted to say it's a very well done, a very exciting concept to explore. I also just wanted to offer, I know Pamela mentioned that your team had been possibly working with some people at JPL. There are groups at JPL, also at Goddard and some of the other NASA centers that have mission design groups that very much welcome interaction with student teams. Mm-hmm. So I would invite you to reach out to us, and perhaps there are mechanisms whereby we could collaborate with you to help answer your questions or refine your concepts as you move forward. Right. So I would suggest you might want to talk to Pamela about how to move forward in that direction if you're interested.
Thanks, Charles. This is Bogdan again. We talked to Charles Barney through a connection through Planetary Science Summer School, and he was willing to help us too, but the more the merrier, I guess, and I appreciate your offer.
Yeah, this is, you're really in the early concept development stage, and it's very exciting, and this is when the fun begins. After you put the initial concept on the table. So I think I'm hoping that you guys derive some really useful information from this interaction with people with scientists and discipline engineers in the room. And thank you very much for for sharing the results of your labors over the last 6 months.
No, thank you very much.
You're welcome.
We're proud to be a part of this.
All right.
Thank you, Pamela. Thank you. Wonderful.